Izzy, and I'm here today to present my work that I've been working on for the past about 6 months here at Reveal. It's about visualizing project evolution using this fancy approach called Poisson Disk Sampling. So first off, one of the fundamental axioms of software development or software engineering is that software changes, and we want to visualize those changes and first off gather those because software can provide us with a massive amount of data that we can get from, for example, versioning systems such as Git. That data contains, for example, the number of commits, the files, including all those changes, which we can categorize as histories and individual versions. And then the question is, how do we take that and visualize that in a way that is understandable for us? And also at a glance, we can gather some information about the entire project. And there are approaches and steps to visualization for software systems. The first step is, what do we even want to visualize? What do we want to focus on? Do we care about non-code artifacts such as issues and pull requests? How do we represent those into visual elements? And we can just start with a very simple idea, which is we take a disk and we can then map properties of that file onto the disk. For example, the radius is the size of the file and the color is the type, and so on. Then we want to place those visual elements that we have into a plane, and there are many different algorithms we can use for that. We can either use a very simple, let's place them all in a row, or then we can group them together so that they take up very little space. We can even try to categorize them into different properties and so on. And we'll talk more about this later. And finally, for evolution in particular, we want to animate the entire visualization so that we have a video of the evolution of the software playing, not in real time, of course, but in time steps that are easily digestible. And so, for example, with our file disks, we can have that a file grows and shrinks over time, depending on the size of the file at that moment in time. So the problem with layout algorithms is that they are difficult to implement, or rather difficult to even think of, because there are a series of problems that we can run into with placing elements into a larger visualization. We also want to care about evolution, so they must support that part of, so they must not move around and be unreadable, basically. So there are three main problems with layout algorithms. The displacement problem is what I just talked about, which is during the evolution, we do not want the file to move around sporadically, and we want to still be able to recognize a file as a single object and not have it go around everywhere. And also at a single time step, we don't want to recalculate the layout completely, because then it might give a completely different layout. Or at the least, we should use a layout algorithm that supports that. Then scalability, of course, software systems can get very, very huge with hundreds of thousands of files and commits. And so we also want to use an algorithm that scales and is not exponential in time complexity. And finally, for another way that we can have cohesive elements or visual elements is just avoid collisions. We don't want files to be placed on top of each other and not be able to, maybe one is hiding behind the other. We don't want that. We just want to visually represent all of them and not have them interact with each other in that way. So we use this Poisson disk algorithm sampling approach, which is sampling is a very simple idea. We have a population and we want to take elements from that population. In this case, we care about positions on a 2D plane. So we want to sample a position for each of our nodes and then have space reserved so that we avoid collisions. And this is essentially what Poisson Disk Sampling does. As a technique, it was inspired by the way that photoreceptors are placed in our retinas. And it's also used in computer graphics for anti-aliasing and supersampling, and also, again, in medicine, because it's a sampling approach that appears in nature as well. How do we compute it? It's actually a very simple algorithm. We start with a single position. Let's call it our active point. We then get a random direction and then try to place a point there. Does it collide with any of our already placed points? If not, then we can place it there. We repeat that. Oh, yeah, and we use a grid in this case for collision detection. There are many collision detection solutions that you can implement. If you just care about the fastest way you can do it for disks of the same radius, which is usually what Poisson Disk Sampling is applied to, then just having as a list means that you have linear time complexity. We can repeat that up to k times, where k is a parameter that we can define. We decided to use k equals 8, but doesn't really matter because it's still linear regardless of what you decide on. And then we can take another element from a queue of all the positions where we have placed files in, or we have placed points, and then continue this process until we have placed enough points or we run out of elements. So we can just repeat that until enough points have been sampled. If all of the attempts fail in a batch, then that is simply a point that we will not try anymore, and we remove it from this active queue. So we have improved or let's say modified this algorithm because it's not exactly perfect for us as it is. First off, we want to remove its random component, so we can do that by simply having a seed in the random number generator for where we determine the direction and the distance to place points at. And also, we want to support disks of various sizes. Ideally, we would like any shape to be able to be placed. So for that, we have to change our collision detection algorithm. We use a KD tree for that, which is pretty simple, runs in logarithmic time. And we can have outputs such as this, where we can mix and match shapes and sizes of whatever we want. So ideally, we could have any visual representation that we want for a file, or even for anything else, really, because we're not just limited to files. This is just a layout algorithm approach. So now let's apply that. We have developed a tool called DVision, where we can use this approach that I just described to place points or to place files and visualize them, and also their evolution. Now, the first question that we asked ourselves when implementing this is, which file do we assign to which disk? Because we know we want a disk for each file, but how do we determine the files to what disks do they represent? Well, if we looked back at our algorithm, or at least the way we designed it, we notice a pattern, which is that the points seem to grow out of our central starting point. So these are just the order in which the points are sampled. So when you start to place objects, you can see that they grow out from the center. And then we can use that to our advantage by simply sorting the files in order of creation time. And that means that the oldest files will be placed first, and the newer files will be placed last. And this means that if we have an animation that shows the files appearing over time, they will grow out of this central core. And then we can see what happens when we try to do that for a larger system. Then we can also do what we said before, which is give each file disk its size and color based on the properties of the file that it represents. And then we have our visualization. For the animation part, remember that we talked about file histories. So each one of these files actually has a history to itself and knows when it was changed and what changes were applied to it. So we can start an animation by showing at each time point, we know what files are present and what files are not. We know at each time step what changes, what files are added, and what files are removed as well. And then we can modify the size and appearance of the disks during the animation. So here in this case, this file went through a versions here, and then grew a little bit while this other file was added. And then we step forward, this other file was added. We step forward again. This file, which was present before, is now gone. This one here. This one is also gone. And then we continue on through the evolution. Now, that was just a simple example. We can apply this to real repositories and see what happens, see what information we can gather. So this is what we have when we sample every file in the JetUML repository. Simply, again, we start from the oldest file, which in this case is the gitignore. If I can find the pointer, yeah. And then all the other files kind of grow out of it. And then here we have some snapshots of the evolution at each point in time. And we can already take some information, some insights from this, such as, for example, you can see after a little bit, this central section of the visualization is kind of unchanged. Nothing is really added or removed there. Well, nothing can be added because new stuff is added outside. So we can already define two main areas. One is the core and one is the outer frontier. And the core is pretty self-explanatory, core parts of the system that don't really change over time, aren't really removed because they're necessary for the system to work. And unless something really drastic happens, they will just remain there. And over time, the outer frontier will just grow. And also, files can be removed from the outer frontier because they're not as necessary as files in the core. Here is a larger example with Visual Studio Code, which has 150,000 commits and 122,000 file histories. And here we can see similar patterns where we have a core, we have the outer frontier, and we also have this kind of ring structure around here that appears shortly after the core is solidified. And then they also kind of don't change that much over time. And we identified them as the early updates to the system, where a lot of files were added all at once. Some files were removed, which creates this ring structure. But the files that are added are early updates to the system, so they are necessary and they don't really change all that much. So we can go step by step, see how at first we can go back. At first, the system is already present because Visual Studio Code was open sourced after it was created. So there is already a big part of the core already there. Then there's always this sort of section or time frame between the core solidifying and the project starting, where a lot of things happen in very little time. And then we have this structure that kind of remains there for the rest of the history. And we can see the rings forming early on, and then the outer frontier still growing over time. Eventually, we don't know, because it hasn't happened yet, will that frontier solidify into a ring, or will it stay there and just keep growing? Or maybe the project will die and nothing will happen. We don't know. Here's another example. This is Argo UML. Here, something interesting happens, where if we look at the video, at one point, the core completely disappears and instead replaced by this kind of inner ring. And that happens when there is, for example, a refactoring and a lot of the early files are removed and there's some replacements already there, and those become the new core part of the system. We can also see that this system at one point kind of stops growing and starts to decay a little bit. Now, obviously, software doesn't decay, it keeps working, but it's interesting how things get very slowly removed, and it really looks like the repository itself is kind of dying. So that's also an interesting observation. So this is our first attempt at a visualization like this, and we wrote a short paper, and what we've learned is that we can visualize large repositories, and then we can solve all three of the problems that we described before. We have scalability, not big issues on that part. Displacement, the elements don't move at all, so that's also nice. And there obviously Poisson Disk Sampling takes care of the collision problem for us, and also gives a good ordering to the elements by providing us with this core frontier separation. Now, for the last part, we started talking with the Zephyr Foundation, which is a real-time operating system that is maintained by the Linux Foundation. It's a very large system with a lot of history of over 10 years, and they wanted us to create a visualization for them, and we decided to try our hand at it with our Poisson Disk Sampling approach. And what we created out of it was this visualization that kind of shows what we talked about before. There is a core, there is some stuff happening, it's not really clear, and then things keep growing around this frontier for a while. So we showed this to Zephyr, and they were interested, but they kind of didn't really see all that much out of it. The last half of that video basically just showed the frontier growing, didn't really show all that much else. And because there was no separation of the different components of Zephyr, it was hard to tell what parts was growing and which parts were not growing. The core maintainer said that they were afraid of the core system not being developed or maintained anymore. But this visualization doesn't really show that or anything to the contrary. So what we did is we started with analyzing the repository, seeing what parts were interesting, and we decided to isolate this boards concept. Now, Zephyr supports a number of boards. From their website, we see that they recently went over the 1,000 board mark from a variety of vendors, and each of those boards has files attached to them that define the configuration and the documentation and some images to see in the documentation as well. So here's what we did. We used the same Poisson Disk Sampling approach, but now we basically encapsulated a single vendor, in this case, TI, and all of the boards that they have are these little slices. Each board has a number of files in it, and also some files that are common to the vendor, to all the boards of the vendor. And we created this simple kind of sunburst-like structure. And then we use the algorithm to lay out all of the vendors. And then we have this nice animation that shows which vendors are growing, which ones are smaller, which ones are larger. And so we think this is quite interesting. And there's definitely some things you can get out of it. For example, you can notice that this ARM one is very big. There's a reason for that, because ARM is also an architecture. It's not just a vendor. So there's a lot of files that are shared to all the ARM boards and not just to the ARM vendor. But that's another story. Then we also said, OK, but we don't want to just show the board files. Let's also show everything else. So we did that. We put everything in the center. And also, just because we had, or actually because of that request from the developers that said, we want to see what the core is doing, we decided let's get the subsystems of the Zephyr operating system, because those are quite important to the functioning of the system, and let's place them all around the center. And so we created this other visualization that shows some other point of view. So not just the boards, which are still there, they're still around, but now we're focusing more on the subsystems, which you can see use the same kind of sunburst structure. So this is a subsystem, Bluetooth drivers, and all the other smaller ones towards the end. And so that was our collaboration. We got a short paper out of it, which is now under review at ASE. What did we learn from that? Well, from our first, we can say, failed attempt, we can say that there is no simple visualization that works for everything. There is no one size fits all. Our approach was quite naive in that way. We found out that different maintainers want different things to be visualized. Some cared more, or stakeholders rather than maintainers would be a better term. Some wanted to see the growing parts of the system because they wanted to advertise that. Some wanted to see, well, what is the actual core of the system doing? Because that's what they were working on, and they wanted to see how that changed over time. And so we can try to isolate those different things, but we always miss some point of view. There were other ways that we could have subdivided the system and seen different information. It just depends on what your point of view is and what you want to focus on. And what finally is just that the basic visualization that we used at first wasn't really all that good for a specialized repository. We actually need to look into the structure, extract information about the domain, and visualize that more thoroughly than just the files. So that was it. Thank you all for listening.